I'm going to talk about extremal correlators in 4 dimensions. This is mostly based on some upcoming work with Alba Grassi and Luigi Tizzano, who are postdocs at Stony Brook. And I'm also going to review the results of several previous works with many collaborators here. I'll give you a few seconds to read the names. This presentation is not going to be chronological. I'm going to maybe give a slightly different route to the final results than was taken historically, but perhaps that would allow me to fit it into 25 minutes. So I'll talk about extremal correlators, some surprising connections to random matrix theory, integrability, and the bootstrap. So historically, or at least mostly in the 90s, supersymmetric gauge theories were viewed as interesting toy models for interesting phenomena in 4 dimensions, such as confinement, symmetry breaking, electric magnetic duality, and so forth. And we've learned a great deal of possible 4-dimensional dynamical phenomena from supersymmetric gauge theories. But my main motivation in this talk is to explore completely, well, more complicated phenomena in quantum field theory using supersymmetric gauge theories. So the first is the properties of perturbation theory, resurgence, the Dyson series, and so on. And what I'm going to emphasize more is what happens when you try to do perturbation theory in excited states, in states with a finite charge density, so for instance. So the main motivation for this work was that, as you'll see recently, there were some heroic computations where people found that even in SU2 gauge theory with supersymmetry, when you study perturbation theory in finite charge density states, you find a new emergent Hooft expansion, a new coupling constant. So there is an emergent new expansion parameter in which there is a non-trivial perturbation theory. And the main goal here would be to give you an explanation of where does that come from through some new duality to random matrix theory. I'll try to give this presentation in as a pedagogical fashion as I can given the time limitations. So the setup, for simplicity, but this is just for, this story is more general, is rank 1 n equals 2 supersymmetric field theories. For instance, SU2 Seiberg-Witten theory will be the main model that we will study. But there are some other examples, such as the maximally supersymmetric n equals 4 supersymmetric Yang-Mills theory with SU2 gauge theory, the free vector multiplicator, Douglas points, and so on. We will focus on the chiral ring operators. The chiral ring operators are the operators that are annihilated by the 2 supercharges, and Chris nicely already mentioned some other BPS operators in n equals 2, so those are not the ones that he talked about. Those are the chiral ring operators. Their dimensions are protected, and they have a U1R charge. Now, these operators form a chiral ring in the sense that their OPE is regular, and in the examples that we're going to study, they generate a free ring where all the operators in the chiral ring are generated by taking products of the generators, of the generator O1 with itself. These were interesting operators historically because there are interesting order parameters for Coulomb branch vacua. So this is the Seiberg-Witten plane, and when you go away from the fixed point, say with 4 hypermultiplets, these operators obtain expectation values, and the conformal symmetry is spontaneously broken. Our interest here is not going to be in trying to go away from the fixed point. Our interest is going to be in measuring correlation functions at the fixed point itself. So of course, there are no non-trivial correlation functions of purely chiral operators, but there are non-trivial correlation functions where there is exactly one anti-chiral operator, which soaks up the dimension or the R charge of the other product of operators. And these are the correlators that I'll call extremal correlators, because that's how they were historically called. These extremal correlators are, on the one hand, very simple, but on the other hand, extremely complicated and rich. And these are perhaps the simplest non-trivial observables in 4 dimensions that we have control over: the complete perturbation theory and non-perturbative corrections. So they're simple in the sense that the space dependence of these correlation functions is easy. The space dependence is exactly known. But they're non-trivial in the sense that the prefactor is a highly non-trivial function of the coupling constant and theta angle, which admits non-perturbative contributions as well as an infinite series of perturbative contributions. So you can analyze questions such as resurgence. You can analyze questions about what happens when the quantum numbers are large, and you're talking about finite charge density states and so on. So these are the questions that we're going to address, of what are the perturbative properties, and what happens when you take the charge density to be fixed, namely you take the charge to be large. We will see that both contain interest in physics. So just to warm up, you can do the free vector multiplet, which is a trivial model, or you can do the maximally supersymmetric Yang-Mills theory, n equals 4 super Yang-Mills, where there is a non-renormalization theorem. So in fact, in these two examples, there is no dependence on the coupling constant, nor on the theta angle, because of some non-renormalization theorems. But once you switch gears to n equals 2, Seiberg-Witten theory, SU2 gauge theory with 4 hypers, you encounter, by brute force, computations and highly non-trivial perturbative expansion. In fact, people have done these computations explicitly with Feynman diagrams. So there is a non-trivial expansion in the gauge coupling, and if you were to study the instanton sectors, there would be some corrections due to instantons as well. So the goal is to try to understand this perturbative series. This is perhaps the simplest four-dimensional correlation function that one has analytic control over, and that's the goal. So the idea is to try to understand these correlation functions of Coulomb branch operators using localization to obtain a somewhat more useful presentation rather than just Feynman diagrams. So the starting point is the four-sphere partition function, which was determined by Pestun in terms of the Nekrasov partition function. So we have an exact result for the four-sphere partition function for such theories such as Seiberg-Witten theory. And what we would like to do is to measure these correlation functions of Coulomb branch operators on the sphere, and then somehow transform that to flat space, which is what we're ultimately interested in, measuring these correlation functions in flat space. So starting from the sphere, one can obtain these correlation functions on the sphere by taking derivatives of the partition function. So if one starts from this expression for the partition function, which is a one-dimensional integral on the Coulomb branch, one can study the two-point functions on the sphere by simply taking derivatives. And then one might be naive, saying that if we know the two-point function on the sphere, where one chiral ring operator is in the north pole and the other is at the south pole, then we simply perform a conformal transformation and we have the flat space answer. But it's a familiar fact that sometimes these transformations from the sphere to flat space have an anomaly. One famous example is the Drucker-Gross-Wilson line, which is non-trivial on the sphere but trivial in flat space. And this is another instance where there is a complicated anomaly. In fact, this anomaly is still being studied, but one could sort of guess one's way and find the right answer without understanding this anomaly in great detail. In fact, the same anomaly plagues two-dimensional conformal field theories and also three-dimensional conformal field theories. But the answer is the following. Instead of mapping these correlation functions from the sphere to flat space straightforwardly, what one does is to take ratios of determinants of certain matrices. So one defines the matrix of derivatives of the four-sphere partition function, and one takes the determinant of this matrix and it divides by a determinant of a smaller block of the same matrix. And such ratios of determinants somehow disentangle all the conformal anomalies and contact terms, and one finds the right answer. So this is the prescription from going from the sphere to what we're ultimately interested in, which are just correlation functions in flat space. One has to take ratios of determinants, and the size of these determinants is determined by the dimension of the operators whose correlation functions you're trying to measure. So that's the prescription, and this prescription works. Now, I want to skip over these two slides, except to mention one very nice observation by this group, where they have shown that even though it might seem like we're assuming conformal invariance for this procedure to make sense, in fact, many results extend to non-conformal field theories, which is another surprising feature here that I do not currently understand. There is one more conclusion that you can draw from this ratio of determinants formula, which is really surprising and connects this field to integrability. From this ratio of determinants formula, it's easy to show that the correlation functions, or more precisely logarithms of the correlation functions, but doesn't matter, satisfy a Toda equation, which is a system of coupled oscillators, which is integrable. So this system of correlation functions of Coulomb branch operators is not a completely independent or unconstrained system. There are some kind of recursion relations relating different correlation functions to each other through an integrable system that you can think about as a system of oscillators connected by springs. And in fact, you can prove directly that this system of correlation functions as a bootstrap problem satisfies this Toda equation, and this was done by these people in some using superconformal word identities, essentially. Okay, so now let's get to the crux of the matter, and let's try to analyze the properties of the correlation functions and the limit of finite charge density. So it's enough to I will drop the instantons for the sake of simplicity, and I will actually justify in a few minutes why this is self-consistent. So we'll study the four-sphere partition function as an integral. It's a completely explicit integral over some special functions, a one-dimensional integral over some special functions, and we'll apply this procedure where we take determinants of derivatives of this function. So the first result that one finds is that the perturbative series, as you may have seen from the first few terms that I quoted before, the perturbative series is badly divergent and has a zero radius of convergence, exactly like we expect in generic quantum field theory. And there were some very nice works that proved exactly that, in fact, all the poles are on the negative Borel axis, and the series is Borel summable. However, the Borel sum of the series is not the same as the full answer. So this is a general lesson in quantum field theory, that the Borel sum of perturbation theory, even if it's Borel summable, has nothing to do with the full answer. In addition, you can test various conjectures from the QCD community about the properties of Padé approximations. There were conjectures in the past that the Padé approximation is exponentially fast converging to the right answer. And so we did the first 100 orders in perturbation theory, and it beautifully works. These are some works of Correlators and Brodsky and many people before. Now let's discuss the limit of finite charge density, where these operators are very big, so they create macroscopic states. It looks like it's an intractable problem because you have to compute huge determinants of some complicated integrals. So one needs a new approach. You might try to do perturbation theory, but as I'll mention, you will soon discover that you cannot. Because if you have a finite charge density, the perturbative coupling constant comes together with J, which is the charge, and the perturbation theory badly diverges. So one needs a new scaling limit, which is one thing we'll do, one needs a new approach to try to do perturbation theory at large J. So the basic trick is a deep formula in mass that was found by Andreev, probably more than 100 years ago, that allows to rewrite this particular class of determinants as random matrix models. And the random matrices here are emergent. We are studying SU2 gauge theory. There are no matrices of which are J by J. But due to this trick, we're able to rewrite the extremal correlation functions exactly in terms of a random matrix model of this type. This random matrix model is a little bit unfamiliar, perhaps, because the eigenvalues are distributed from 0 to infinity. But otherwise, it's very standard. There is a van der Monde, and the potential is a confining potential for the eigenvalues, like in the examples you've all seen. And the potential is slightly complicated, but it's known exactly. There is a logarithmic correction and a confining potential. It's a very standard type of matrix model, which people have studied for many years in the matrix model community. Since the eigenvalues are distributed from 0 to infinity, this is not the standard Hermitian ensemble. It's called the Wishart-Laguerre ensemble, chiral ensemble. That's one name in the literature. Another name for this thing in the literature is the Altland-Zinnbauer ensemble. This kind of ensemble of random matrices appeared in several previous instances in physics. One in QCD. There's this old work of Verbaschat, who found the exact same type of matrix models as descriptions of the vacuum of QCD. And also, I think today there is a paper of Edward Witten and Douglas Stanford where this exact ensemble appears in the context of integrating over super Riemann surfaces. So they appear in several applications. And here the appearance of this matrix model is particularly interesting because it's really reminiscent of the eigenstate thermalization hypothesis and its connection to random matrix theory, where after all just studying correlation functions in heavy states, and we see a random matrix theory emerging, where the size of the matrix is determined by the charge density, or by the total charge of the state. So it's really reminiscent of that. Now this matrix model is a little complicated because there is this complicated special function for the potential of the eigenvalues But if you take the charge to be very large, this completely drops out, and it boils down to something much simpler. So if you take the charge to be very large, you can simplify the matrix model by just keeping these two pieces, the confining potential and the logarithmic piece. And the reason being is that the density of the eigenvalues is the so-called Marchenko-Pasteur formula, and it shows that the typical eigenvalues of this matrix are of order, oh, this is a mistake. They are of order J. Everywhere n should be replaced by j. I'm sorry for this typo. So the typical eigenvalues are very large. They're of the order of the total charge, and therefore you can basically simplify the potential self-consistently. And so you need to solve a much simpler random matrix model if you want to understand the limit of fixed coupling constant and huge charge. That's one limit that you can study, where the coupling constant is fixed and you take the charge to infinity. You get a very simple matrix model, which you can solve, and you can compute the first few corrections at large charge. And there is a very interesting physics in this limit of fixed coupling constant and large charge. There is a recent work by Hellerman, Maeda, Orlando, Refert, and Watanabe, who argued that in this limit of fixed coupling constant and large charge, you get simply a Goldstone boson theory. That the physics in this limit is described by an axion-dilaton Goldstone boson, and they write a Lagrangian, a non-relativistic Goldstone boson Lagrangian. And fantastically, this exactly matches the predictions of that Goldstone boson theory. So this is really like in QCD, that the Goldstone boson theory of pions is matched by the chiral matrix model. It's really in the same spirit. However, a much more intricate limit, I should say, or a surprising limit, is a new double scaling limit that is completely unexpected, where you take the coupling constant times the charge fixed. So we're talking about SU2 gauge theory, but there is now a 't Hooft coupling, or a 't Hooft-like coupling. The random matrix model shows immediately that such a limit is natural, because if you take the coupling constant to scale like the size of the matrix, then the first term here is exactly how you write large N matrix models. So clearly there is, and this is like a non-planar correction. So from the random matrix model, it immediately follows that there is a new coupling constant where G Young Mills squared times the charge is kept fixed. This is this limit. And there is a genus expansion. So there is a genus expansion in SU2 gauge theory. Now, in some really remarkable work by Bourget, Rodriguez, Gomez, and Russo, and then Beccaria, who extended it to 10 loops, what they've done is to start from ordinary perturbation theory, including the charge density, and they've shown that, in fact, the perturbation theory reorganizes itself into an expansion in this parameter, G Young Mills squared times the charge. And so what I've told you makes this observation clear, because there is a random matrix, and in terms of the random matrix model, this expansion is nothing but the 't Hooft expansion, because we now have emergent J by J matrices, and the potential for the eigenvalues goes like N, or like J, sorry, again. So this explains why there is such an expansion in the 't Hooft coupling, and we can use the random matrix model to solve this problem completely. We can determine the genus 0 and genus 1 partition function by just a standard computation in large N random matrix models. So this is, for instance, the leading behavior, and then there is a series that you can find for the subleading behavior, the first non-planar correction. It's of course tempting to ask if ordinary QCD SU2 gauge theory admits such a double scaling limit. This is currently unknown, but in the context of the supersymmetric theory, it appears to be true that there is a new 't Hooft coupling in that limit. So the dictionary is that there is a double scaling limit at large charge, and that corresponds to the 't Hooft expansion, where the charge is replaced by the rank of the matrix, and the 't Hooft coupling is G Young Mills squared times the total charge. Now, I have neglected gauge instantons, as you remember, from the matrix models, but now this is justified. This is the same argument as in the old large N model days, where people said that gauge theory instantons are subleading at large N, which is true. And the same is true here. Of course, there is the subtle phenomenon that gauge instantons can fractionalize, and it would be interesting if there is something like that also here. But the naive gauge instantons are suppressed. So this connection between extremal correlation functions, resurgence, integrability, and random matrix theory is completely general, though I've only presented it for SU2 gauge theory. In fact, you can prove that for every n equals 2 superconformal field theory, there is an associated integrable model which generalizes the Toda chain. And there is an associated random matrix model which computes their extremal correlators, though we haven't studied the most general cases. And this gives an interesting glimpse into properties of perturbation theory in non-trivial macroscopic states. Surprisingly, there emerges a new 't Hooft-like coupling, and the duality that we have shown with the random matrix model explains sort of technically why this is correct, because it can be recast as the 't Hooft expansion of a random matrix model of a sort that is much more familiar. And it makes some contact with the eigenstate thermalization hypothesis, which I am not going to say much about due to lack of time. Thank you very much.
Thank you very much. There's time for questions.
So is the potential in your J by J random matrix theory dependent or universal?
These two pieces are completely universal. This depends on the theory. This piece depends on the theory. But in the limit of large charge, it always drops out. So the large charge predictions are always universal, and they would match the Goldstone boson, the non-relativistic Goldstone boson theory. However, if you are interested in extracting detailed information in the new double scaling limit, in the new 't Hooft limit, then you have to take into account this particular form. But it's computable for every given, it's computable in principle for every supersymmetric field theory by using localization. So the potential here is known exactly. Unlike in generic eigenstate thermalization hypothesis type of things, where the potential is only conjectured or assumed, here the potential is known exactly.
Other questions? No, everybody seems satisfied. Thank you very much again.